Let's see a result that is quite important in modular arithmetic. And so this is called Fermat's little theorem. And it says the following. If p is a prime number and a is an integer not divisible by p, then a to the p minus 1 is congruent to 1 mod p. And so this will give you a very quick way of, for example, calculating powers when you're doing mod prime. So as an example, and we'll see an example of that later, but for now, what this is saying is that, for example, if you take 2 to the power of 4 will be congruent to 1 mod 5, so 5 is prime. This is 5 minus 1. So if you do 2 times 2, 4, times 2, 8, times 2, 16, and so 16 is congruent to 1 mod 5. Another example is 3 to the power of 6 will be congruent to 1 mod 7, right? And I mean, this is just what it means. But let's see a short proof, or at least a sketch of the proof of why this is the case, right? Okay, so here we wanting to show that a to the p minus 1 congruent to 1 mod p. So the idea is the following. Consider the following list. A, 2a, 3a. Imagine that you list out all the multiples of a. So a, 2a, 3a up to p minus 1, right? So the first point is that no two of these from this list, can be congruent modulo p. And here, of course, remember that p does not divide a, so we need that. Now, why is this the case? Well, so why? Suppose that two of them are. So suppose, for example, that IA is congruent to JA mod P. So suppose that there is I and J, so that two of these, so maybe I is equal to 3 and J is equal to 10. So let's say that two of these are congruent. So if that happens, then you can subtract by JA and factor out the A, and that means that A times I minus J is congruent to 0 mod P. Okay? Now, since P does not divide A, and P is prime, that means that A and P are coprime, which means that A is invertible modulo P. So you can multiply by its inverse, and so this implies that I minus J is congruent to 0 mod P, which means that I is congruent to J mod P. Okay, but both I and J, they are, so here I and J are the numbers that appear here. They're all in between 1 and P minus 1. So that means that, so when you divide I and J by P, you get remainder I, you get remainder J here. But they are, so they get the same remainder, but they are how do you say, they are in between 1 and P minus 1, which means that I has to be equal to J. Now, okay, so this shows that no two of these are congruent. So if you take two of, if they were equal, they would only when you do like 3a equal to 3a. So there's no way for two of these to be congruent to each other. And you actually have p of them here. And they are all numbers between 1 and p. Thus, what does that mean? Thus, this list here is just a permutation, of the list 1, 2, up to p minus 1. Because, once again, what are the remainders that you can have? They are the numbers between 1 and p minus 1. And we're saying that these all have to be distinct remainders between 1 and p minus 1. So that means that these numbers have to be the exact same as these numbers, but maybe in some shifted order. So maybe this one is 7, this one is 2, and so on. But all the numbers between 1 and p minus 1 have to appear here. Now, what that means is that if you multiply this list, so a times 2a times, and you multiply this, p minus 1a, it needs to be the same as if you multiply this list over here, because they're the same list. So 1 times 2 to p minus 1. Okay, on the right here, this is just p minus 1 factorial. And on the left, you can also factor out the a. So, or not factor out the, well, I mean, yeah, sort of like just separate it, decompose here. This will be a to the p minus 1, because it appears p minus 1 times p minus 1 factorial. And so this means that we get this identity here, a to the p minus 1 factorial, congruent to p minus 1 factorial mod p. But p minus 1 factorial, so it's all the numbers up to p minus 1. So none of these numbers are divisible by p, right? Because p is prime, and also they're like in between 0 and p, so even before that. So that means that this is not divisible by p, which means that it needs to be co-prime with p, which means that this has an inverse. So p minus 1 factorial has some inverse. So we can multiply by the inverse of p minus 1 factorial on both sides. And thus, we get a to the p minus 1 congruent to 1 mod p. And so that proves Fermat's little theorem. And so the last thing we'll do in this video, let's use Fermat's little theorem to compute a large power quickly and efficiently. So let's say that we want to compute 2 to the power of 43,210 mod 101. And so what's good here is that 101 is prime, which means that by Fermat's little theorem, 2 to the power of 100, we know that it's congruent to 1 mod 101. And now what you do is you just take what you're interested in, so 2 to the power of 43,210. So you can write this as 2 to the power of 432 times 100 plus 10. So you take this number here, the exponent, and divide it by 100. So you can write this as 432 times 100 plus 10. And so this, you can then rewrite it as 2 to the power of 100, 432 times 2 to the 10. Now we saw that 2 to the 100 is congruent to 1, so this is actually just a 1 to the power of 432, but that's easy, it's just going to be 1, right, times 2 to the 10. which means that this is just 2 to the 10 mod 101, right? And 2 to the 10, we know it's not, so 2 to the 10 is just 1024. And now we can just compute this mod 101. So if you divide by 101, and so this is not too bad, you can just do it by hand. If you divide this by 101, you're going to get a remainder of 14 mod 101, which means that so 2 to the 43,210 is going to be congruent to 14 mod 101, and this you can really do by hand. I mean, all these calculations here can be done quite quickly by hand. So taking mod primes, powers mod prime can be very quick with Fermat's little theorem.